research, what we have done is we have integrated the machine learning with our existing methods. So in our existing radar, which is FPGA based platform signal processor, where SDL through SDL signal processor, it was basically CFAR working on the FFT. Their clutter mitigation accuracy was not that good. So what we have done is we have used the machine learning method to improve upon that accuracy. So I will start with the outline where I will introduce by stating the problem statement. Okay, and what was the problem with the existing system, and what was the solution we have provided, and then how we have collected the data, and how we prepared the data, and then the modeling, then evaluation results I will share, and then I will conclude my presentation. So this was the problem statement. So it was, as I mentioned, the CFAR and FFT based signal processor was facing the problem with clutter mitigation. The accuracy was not that good. So problem statement was to discriminate between the ground clutter and the target for perimeter surveillance radar. So limitation was because of the fact Doppler information was the only discrimination factor which was separating the clutter from the target. So to solve this problem, what we have done is we have created some new features where clutter can be discriminated from the target in a better way, and we have used machine learning method to find the solution for that and integrate with the existing system. So as you can see in the flow, we have collected the data, then data is converted into some particular format. Then we have extracted the feature, and we have done the labeling, which is the manual labeling we have done. And then feature analysis is done. So unless those features were okay, we were continued and we were trying. So once we got our features, then we trained our model, and then we evaluated. And then finally, we compared all those models, which one to integrate with our existing system. So in our data collection process, this is a very simplified block diagram where a signal processor and a personal computer, they were connected through Ethernet switch. And after the down conversion, when data is in the baseband, that raw IQ data, it is sent as UDP packets, where it is saved on the personal computer in the PCAP files. So those PCAP files we can easily save, and we can easily work with those files. And to remove the bias which is generated from either from various parameters, what we have done is we have collected the data from two different sites at different time, and we have used two systems also. So this is to average out all the bias which was inherent in the system. So this is the table which is representing our PCAP file size, how many number of scans we have collected, and what was the day, and what was the site and the system ID. So this is the Google Map view of the two sites where we have collected our data. So the red dot represents the radar location, and red lines represents the boundary within which our sector scan was happening, and the yellow line are representing the clutter boundary. So this same image in the radar, it will look like this. So where you can see on the clutter boundary, the strong reflection of the power is visible. So this is the radar clutter image on the dB scale, and this is our overall data preparation process flow. So where once PCAP file is saved on the personal computer, so then we have extracted that PCAP file into the raw file. So this for this we have used the Wireshark software, which is open source software, and the next 5 steps we have done in the MATLAB. So where raw files are directly read into MATLAB, where radar data cubes are created. So once those data radar data cubes are created, which represents in the fast time, slow time, and how many number of pulses we have used. So radar data cubes are represented in those sort of dimensions. So once radar data cubes are ready, then we generated the feature, and for each feature we have generated a two-dimensional scan matrix for each scan, where on the one axis it will represents the azimuth and other axis it will represents the range. And once that 2D scan matrix is created for all the data, then manual labeling is done in the MATLAB itself, and finally it is converted into a CSV file, which can be processed in the Python, and where we have used the Google Colab software for uh, training our models and testing our models. So this is a very typical view of one scan where we have created our radar data cube. And these are the features which we have created and which helped us in discriminating the clutter from the target in better way. So, so the first feature is the FDM threshold. So this threshold represents the each Doppler band. We have taken the moving average over the scan. So this represents the moving average power over the scan for each band. Then we have the fan threshold, which is the probability of that any particular range cell being either clutter or target. So what we have done in this feature, it exploits the static nature of the clutter. So if the clutter is static, so that means the same detection is going to happen through the CFAR all the time. So that means if we can make some sort of count uh, over the scan, and then we can find out whether it is still coming in the same range cell over the scan or it is on the move. So this way we have calculated the probability. Then there is a power decay, which is nothing but the ratio of the power between two neighbor range cell. And there is a sigma, which represents the spectral Doppler width of a particular range cell. And then there is a signal to noise ratio, which we have calculated from the FFT by taking the ratio of its peak power to the average noise floor power by removing the DC component, which are the extreme Doppler bins in the FFT. And then there is a D by S, which is a complex ratio of our difference channel to the sum channel, and it is used to indicate the angular error in the monopulse application. Then there is a detection. So in this detection, which represents the CFAR output. So wherever detection is there in the 2D matrix, it will be represented as +1. Where detection is not there, that range cell is marked as -1. So next step was data labeling. So this data labeling, as I mentioned, we have converted in each scan into two-dimensional matrix. So once we have that, then we have used these 5 points or factors in the consideration to do the manual data labeling. So one sample is shown where one scan data is labeled. So the left-hand side shows the data 2D scan, which is created from the MATLAB, and then right-hand side it is the labeled target data. So detection range cell from the conventional method CFAR itself is a big factor in deciding whether it is a target or not, but also the alignment of the expected target path, which is our control target, that also we have taken into consideration. Next is the location of the fixed clutter, which we can see from our clutter map of the radar image, and also the previous location of the label target. So because target is moving, it is a control target. So based upon its previous location, we have considered that also while labeling our data, and also intuition from the other features. So once our data labeling is done, so next challenge was the class imbalance issue. So you can see before handling this class imbalance, there was a massive uh, 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 gap between the number of samples from one class to another. So what we have done in this, we have separated our data into three categories. So first is the non-detection. These are the empty range cells, you can say. So where detection is not there and we have given it label as 0. The next is where detection has happened, but we have not labeled that data. So that is actually clutter. That is not your target, that is something else. So that is the clutter. And the final where we have labeled our data, that is our target. So once we have get rid of these non-detections, then our class imbalance is improved. So, but still this is not good enough. So what another technique we have used to deal with this class imbalance, which is still there. So that I will represent in the next slides. After removing this class, non-detection class, we have done the central tendency analysis of the feature, where the upper table represents uh, the target class and the bottom table represents the clutter. So as you can see, the label for the upper is always 1 and for the lower one it is always 0. And if you see this fan threshold, so it is in the negative side for the target and always on the positive side for the clutter. So this we have converted into some sort of probability by normalizing this factor. So as you can see other features also. So for better understanding, what we have done is we have done the p-value analysis, and we have also, to remove the redundancy in the, from the features, we have done the correlation also. So with the both, the results are here, and the minimum, the worst case p-value, which is for the SNR feature, but for other features, p-value is actually less than 2%. So which is quite good. So once we have done the analysis, then we have trained the three models: decision tree, support vector machine, and ANN. So this ANN is actually very shallow kind of neural network. So for the and the platform which we used is Google Colab and Python. So entropy for the decision tree, we have used the Gini index, and max depth, which we have found out experimentally, was fixed to 5, and max leaf node is equal to 7. For the support vector machine parameters, the kernel selection also we have determined experimentally, which I explain in the next slides. And the C parameter is fixed to, which is a regulation parameter, it is fixed to 1, and gamma parameter selection is also taken as 1. And same for the ANN, optimizer Adam is selected, hidden layers 2 were used with ReLU as the activation function, and the output is sigmoid. So number of epoch 30 and batch size of 100 is used. So to find out the decision tree depth, what is the optimal depth for that decision tree, what we have done is we have designed one experiment where on the one side we have taken the accuracy, and on the other side we have tried out different depth of the decision tree. So as what we have found out is, when it is reaching to 5 or 6, our accuracy, it was saturating. So that is why we have taken the accuracy equal to 5. And for the support vector machine, these two parameters are quite important. So both parameters actually controls our boundary shape. So it will define how wiggly or how straight our boundary will be. So C regulation parameter basically will decide that, and gamma regulation parameter will decide how many samples around that boundary we are going to include in our decisions. So to create that decision boundary, how much of the samples you want to include near that boundary. To find out which of the kernel is best fit for our data, so what we have done is we have used all 4 kind of kernels, and on the one side we have the accuracy on the y-axis, and on the x-axis what we have done is C regulation parameter. We have taken a different value, and through the experiment we have found out for linear kernel the accuracy is actually not affected by the C regulation parameter. So this means the data, it is already quite separated in the linear kernel space. So that is why we have selected the linear kernel for our support vector machine parameter setting. And for the ANN, the experiment which we have done to find out which of the network is giving us the better accuracy. So this architecture for hidden layer 1 and 2, what will be the depth of the both layer? So different architecture we have tried, and these are the results which we have get. So from here we have selected the best architectures, number 9 and 15, which are giving the most accuracy for the 2 hidden layer architecture. So once we have decided the parameter and configuration of our models, so still there is one issue we were facing is because still there is a class imbalance between the clutter and the target class. So clutter class sample size is 9 times of the target class. So we have come up with a solution where we have made the subset combinations as 9 sets, where the target class is combined with each of the subset of the clutter class. So this way we have now 9 training sets for model training and evaluation. And further, for each set, what we have done is we have used the k-fold validation technique. So this k-fold validation technique, the ratio between training and evaluation, we have taken 75 and 25. So that means 9 sets, and within 9 sets there are 4 variants for the k-fold validation sets. So that means total 36 sets are used for training the each model. So so this means total the average accuracy which we can find is over these 36 experiments, and then we can compare our model. Also, what we have done is we have done some special discovery test on the tangential data, where we want to find out the limitation of our model, which was expected, because when target is moving tangential with respect to the radar, so what will happen, its property will become similar to the clutter, which is static in nature, because the relative motion between the radar and the target will be very slow. So from this data, what we intended to find out is the how much accuracy drop is there for the each of the model. So these are the results of those 36 experiments which we have conducted for each of the model. So for decision tree, we got the minimum accuracy of 55 and the maximum is 98. So on average, if you see, we got the 84% of the accuracy. And also when it is done on the tangential data, where we expected the accuracy to drop, the average accuracy dropped to 75%. So same results we have got for the support vector machine also, but it has given us the better result than the decision tree, where the minimum accuracy we got is 70% and the maximum is 98. On average it was 87%. And after testing it on the tangential data, the average accuracy dropped to 80%. And also confusion matrix is also shown. And this is for the ANN validation, where we got the average accuracy of 88%, and on tangential data it dropped to 79%. And also from our data, where all the detections were there, so we can also find out the accuracy of our CFAR, which is the ratio of number of true label target and the total number of detections. So this was coming around 9%. So finally, we can compare all our models, including the CFAR also. So where the accuracy was less than 10%, but when we used our machine learning methods, where accuracy was more than, on average, it was more than 84%. And here also, their target drop ratio is also represented for each of the model in percentage. So what target drop ratio represents here, it is nothing but the false negatives. So these false negatives are important because in critical application, false negative means you are losing the target for one or two scans in between. So that can lead to drop of the target. So this was the least for the SVM what we have seen, and the most it was for the decision tree. Uh, so this is the model limitation which we were trying to find out from our tangential data, and this we have represented in the table how much accuracy on average we got, and how much we got on the regular data, how much we got on the tangential data. And the average accuracy drop, it was least for the support vector machine, and it was maximum for our decision tree. And also, apart from this tangential data, we also have the limitation. The data collection which we have done is, it is unmodulated waveform was used. So this same model might not work for the modulated waveform. And the control target which was used was walking man only. So for other types of targets, we have to recollect the data and remodel and retrain our models. So the same model might not work for the other types of target. Next, final is to select between the models, which one to integrate with our existing system. So our existing system is FPGA based platform embedded system, in which entire coding is done in the VSTL. So that means the best option to integrate with our existing system is the decision tree, because it can be written directly in the HDL itself, whereas for support vector machine or for ANN, you need either model conversion to C++ or MATLAB. So C to HDL, or you write the model in MATLAB and again convert into HDL. So those sort of things are required. So this is a very in the table we have done the comparison where the integration effort level and computation resources, qualitative differentiation is done, and also the average accuracy and the target drop ratio is used. So as we can see, the accuracy still it is close to the other model for the decision tree, but it is very easy and it requires the least amount of resources to integrate with our existing system. So that is why we opted for the decision tree. So in the conclusion, what we have seen is the feature correlation was less than 33%. The p-value in worst case we have seen only 12%, and the model accuracy on average it was more than 84%. And whereas the previous method CFAR accuracy in the clutter mitigation point of view, it was only around 10%. So by looking at these statistics, so we can say after integrating, we got the significant improvement in our clutter mitigation. So for the future work, one is the raw IQ size is very large. So those PCAP file which we have collected. So this radar was having 256 number of pulses in one CPI. So that means a huge amount of data we have collected. So one future work can be to create those features in the embedded system itself and then send only those features outside. So there all those pulses will be integrated and your size will be reduced by great margin. Another thing is data labeling can be automated. So what we have done is we have manually labeled the data, but we can use and apply some sort of GPS log based technique where data labeling can be done automatically. And also the limitations on which I have already explained, those can be improved. So for example, is tangential target improvement and modulated radar waveform can be used, and the same experiment can be done for the other kind of targets. So that was my research. So thank you for your time. So any question is there, so you can ask me, please.